Okay, this time we're going to do some quick tests on the motor. One thing I'm going to do is some speed tests. How fast can you get away with stepping this thing? I'm going to try to measure torque if I can get my mechanical setup all done and everything. May have to skip that, I don't know. And we're going to try to do drive the stepper straight out of a pick without any supporting circuitry. No H-bridge, and mainly no diodes for protection at all. So just a bare pick. We'll just see how that goes. So okay, what I've done is our little arm on the motor. See, I've got a screw and I've got a little hex standoff mounted on our servo arm. That's going to add a little bit of mass. So we're going to do a set of tests spinning this guy around with the hex nut on there, and a set of tests with it off, and see if that makes any difference. So right now we're going to do a little bit of half stepping. I believe this is set up for. Give it a shot. First time doesn't count. I hope you can see this guy go around. Okay, so there he made one trip around. It's doing exactly 40 steps. Alright, so here's the shot for half stepping on our slowest speed. And our slowest speed, and the cursor's on here, and the difference is 49.8 milliseconds. So it should go back to its starting position each time, and we see at that speed it's doing a little faster, and I'll show you on the scope. Alright, now half stepping and our speed 2 turns out to be right there, and that is 42.3 milliseconds. And we'll step up to the next speed and we see, oh, it didn't quite make it. It only takes about not even a quarter of the steps. And we'll show that on the scope and show what that speed is. Our speed 3 for half stepping, and that is 34.8 milliseconds. And the next speed up, it doesn't even move. You can tell by the diode, by the LEDs, it's just it's pretty blazingly fast. And speed 4, that's 40 steps in a period of 27.3 milliseconds. So these are, the absolute numbers don't really mean much. This is all relative. So just to show you that we are stepping faster every time. So we'll go back to the first slow speed that worked and see if he doesn't return. Yep. So, and then the second speed. So he's acting pretty consistently. The next speed up doesn't move at all. Okay, now we'll pull the jumper and we'll do full stepping. And once again, first time doesn't count because it's got to get lined up to the signal. Well, there he did make it, didn't he? Must have been in an agreeable position. Okay, this is the slow speed for full stepping, and he makes it all the way around. Go next speed up. Well, let's look at the look at that first speed on the scope. Okay, this is full stepping or two-phase stepping. This is the slowest speed, and this is 48.5 milliseconds. Now we'll look at the second speed I have here. Oh, and he's doing the same thing, just going a few steps. Let's look at that on the scope. So here is speed 2 that we're using, and that comes out to be 42.8 milliseconds. And we do the third speed here, and he takes a step but comes back to the beginning. By the time he moves once, it's already clocked around to his original position, so he backs up to it. So there you see you do have a limit. There he is, the slow speed going all the way around. So there you see there is a limit to how fast you can drive these little guys. Here's speed 3 for full wave stepping, full stepping, and this is 38. It's at 39.3 milliseconds. Now I'll take the screw and hex standoff off of the arm, and we'll see if there's any difference. So now we're still in this is still full stepping. Now we'll do our original speed. Of course, with less mass, we should have no problem there. She goes all the way around. Now this is speed 2, and this is the speed where it only moved a little ways. He made it all the way around. This is the speed where he moved a touch and recovered back to the starting point. But he's going all the way around. Hope you can see that, because it's going around pretty fast. And the fourth speed, which you haven't looked at, and he's making that also. And our fourth and our fastest speed at full wave stepping is 35.5 milliseconds. So each of those is one revolution. So without the weight, half stepping has no problem with any of those speeds. So it shows, your load makes a difference. Your mechanical load makes a big difference. So now I'm going to go back to full step. Now we're going to go back to half stepping rather. Okay, first time doesn't count, but it made it. There it's making it around. Second speed, half stepping, and half stepping, that's the 4th speed. It doesn't quite make it. Can't keep up. Is this going around? I can't. Yeah, that one's turning. Speed 4, no. Speed 3. It is going around. Boy, it's hard to see. Probably need more frames per. It's going around, but might need more frames per second video to see it well on the camera. So okay, well that's a little demonstration of the importance of determining if you can drive your mechanical load or not. Okay, here's our setup to do the deceleration test. Now what the code's doing in this case is it initially spins up the motor for 5 revolutions, and then during that first 5 revolutions it's accelerating the step pulses. They start coming faster and faster. Then for the last rotation it holds it steady, quits accelerating, keeps issuing pulses at the rate it was at the end of the acceleration period, and then it abruptly stops after that revolution is over. So now if it successfully stopped, you should see the little arm here show up at the position it started from. And if it doesn't, you'll see it go some distance past its point. Now for all cases, every switch position increases the amount that is subtracted from the delay between pulse periods. So as you go up, as you select a higher switch, you go faster and faster. Now all the accelerations are within the limits that we looked at on the acceleration test. So anyway, all that BS aside, let's see if we can make this thing go. Now the first thing it does when you turn it on, it sets a position in case the motor is not aligned to what it wants to start at. So it sets an initial motor pulse and waits a couple seconds so you can see where the arm is starting at, and then it runs the test. So there'll be a little bit of a pause, and I have to hold on to the thing. Let's see if I can work around the camera. I have to work around this. I have to hold on to the motor so it doesn't torque itself. Got the weight, got the screw and hex standoff on the end. So let's try the first position. There it positioned itself to start, and there it ends where it started. So that successfully stopped at the end of the 6 rotations. Here's the second speed. It also stopped at the correct position. Here's speed 3. It's stopping at the correct position. Here's the 4th speed. Whoop, went past it. So there's an example of stopping your motor pulses, but the motor continues on. And that continued for a quarter turn. There it is again, another quarter turn. I'll drop back down to the previous slower speed, and here he ends up where he should, or where we want him to. And then I'll go back to this is the speed it can't handle, and he steps a little bit, almost a quarter turn beyond where he should stop. So okay, there you see a little demonstration of inertia, the motor not stopping where it should, and it probably jumps to the next location that this drive is setting it to, and it stops there after it loses a little momentum from overshooting. So let's look at some of this on the scope and just show you that times are actually increasing. Okay, on the scope I just have the A1 drive up here on channel 1 and the B1 drive. So it looks like it's light on pulses, but it's actually not. You can't see all the states with the A2 and B2 missing. But this is just going to show our acceleration and how that's accomplished. So basically, this is the lowest speed I have, and pick a pulse at random. Whoops, widen that out a little. And that's we're on excuse me, we're on 2 milliseconds per division. It's 246, just under 7. If we scroll left a few, see it's 246, just barely over 6. So the pulses are getting shorter. And then at the end, the last rotation, the pulses are all about 2 milliseconds. So he's 2. He's 2. This guy's 2. So with the last rotation, the acceleration stops, and then of course it abruptly cuts off. So that's the basic way we're driving the motor. Accelerate it up and stop it real quick, and that's the time period for our slowest 1 revolution. Okay, here we have our cursor set up to encapsulate the whole period of the acceleration and the steady drive, and we have a difference of that's 440 milliseconds. So let's go to our second step. Here's our second speed, where it still where it still operates correctly, and you can see our total period for driving it has decreased, and that's to 409 milliseconds. Now we'll do the third speed. Okay, here's the speed for my third little switch, where the motor was still reliably stopping. We can adjust the cursor, and we see it's increased to, or decreased to 365 milliseconds. You can really see the acceleration here. The pulse is getting narrower and narrower and narrower. Then right at the end they hold steady. And here's the speed where the motor overshoots. See, we have gotten faster, and that's a total time of 325 milliseconds. So now these times are just for comparison. Their absolute values really don't mean much. You'll be different. What these speeds are will be different for the motor you're using. So this is just basically a demonstration that that you have to watch out for this effect if you're if you're wanting to run at high speeds. Okay, we've got our little pick here. It's a 16F 84A, and we're going to drive our motor straight off the pins. No external circuitry, no protection diodes. The motor's hooked up right here. These are my scope probes right here. There's nothing else on these pins except the motor. So let's turn her on and see if it drives a motor. And there it goes. And so there we're full stepping counterclockwise. And so that looks perfectly normal. Let's look at the waveform. Alright, so here's our waveform for the 16F84A. I've got measurements turned on, the cursor's turned on. Here they have this positive overshoot, and its value is 5.8 volts. Now that's a half a volt higher than the spec says you can drive a pin. Now when you first start a chip and it's driving the motor, the square waves look pretty good. After a while it degrades. I'll start it running here. It degrades the pins, but it keeps driving the motor for a pretty good while. This is just the A1 output from the pick. There's our spike there, and you can see what you see what he's doing. He's oscillating like crazy. So it's degrading I would guess the base emitter junction inside the pick. And it's making it's increasing its capacitance, apparently. Just a guess. And this thing is all over the map. See, that waveform is just horrible. What's happening is the output's oscillating. See if I can get a single shot here. Get persistence. There we go. The output is oscillating like crazy. It's driving the motor. The motor's going pretty well, but this output is not going to last. This is not going to last forever. So while it looks good, come on, baby, trigger. So while it looks good, driving the motor, the signal coming out of it is just horrendous, and we're overshooting quite a bit, by at least half a volt, and that's not good for the pick at all. Not much trouble with undershoot for some reason. There is a little bit of an undershoot, but it's manageable. This level here is floating above ground. That's not ground. If I go back to my cursor and let me look at B, I'll crank that up. And B is that's half a volt, 550 millivolts. So that's above ground. These negative spikes are okay. There are some bigger negative spikes, but this is not good for the pick at all. And so while it looks good, makes a good demonstration that you can say you're driving your motor just fine. And there he's going around, still half stepping or full stepping merrily away. The signals look horrible, and this chip's not gonna keep functioning this way forever. So the reason I'm showing you this, I forgot to mention, there was a YouTube video of this, and a guy driving his motor this way, and saying it's perfectly fine to do, but from the waveforms, no, I wouldn't count on this at all. It's gonna start screwing up eventually, and it's gonna ruin your output drivers on your PIC or any other processor driving this naked. So motor looks happy, but the chip's not happy.